Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should make your brain gently expand with the sheer scale of it all. Right now, as you're listening, somewhere in the universe, billions upon billions of stars are burning, each a potential sun to its own retinue of planets. Our own Milky Way galaxy, a swirling disk of light and dust, contains an estimated 100 to 400 billion stars. And that's just our galaxy. When astronomers point their most powerful telescopes at tiny, seemingly empty patches of sky, they don't find emptiness. They find thousands upon thousands of other galaxies, each one a cosmic island teeming with its own stellar populations. The observable universe, that sphere of reality from which light has had time to reach us, is thought to contain roughly 2 trillion such galaxies. Now, let's do some quick mind-boggling arithmetic. If we take a conservative estimate of 100 billion stars per galaxy and multiply that by 2 trillion galaxies, we arrive at a number that is almost incomprehensible. 2 Earths 10 to the 23, or 200 sextillion stars. That's a 2 followed by 23 zeros. For every single grain of sand on every beach on Earth, there are more than 10,000 stars out there. The sheer statistical probability, it would seem, dictates that Earth-like planets capable of harbouring life should be incredibly common. If even a tiny fraction of these stars host planets, and an even tinier fraction of those planets are roughly Earth-sized and in the right orbital zone, we should be swimming in a cosmic ocean of potential homes. So why haven't we found them? Why, despite all this incredible vastness, does Earth still feel so profoundly, almost impossibly unique? This is the core mystery we'll explore, peeling back layers of scientific understanding to reveal the astonishingly intricate dance of cosmic coincidence and physical laws that make our existence possible, and perhaps incredibly rare. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with a number that genuinely defies intuition. The number of possible outcomes in a truly random lottery, where the odds are stacked against you in a way that makes winning seem impossible. But here's the thing. The universe isn't just a big lottery. It's a lottery where the rules of the game are incredibly complex, and the definition of winning, finding another Earth-like planet, is far more nuanced than simply picking the right numbers. We're talking about a cosmic scale of numbers so vast that our brains can barely grasp them. Yet even within that immensity, the specific conditions for Earth-like are so precise that they quickly whittle down the seemingly infinite possibilities. Everyone knows the universe is big, but let's get specific about what big truly means when we're talking about the search for other worlds. As we just touched upon, our own Milky Way galaxy alone is home to hundreds of billions of stars, each a potential sun. Imagine for a moment that our galaxy is a vast cosmic beach. Each grain of sand on that beach represents a star. Now, consider that for every grain of sand on all the beaches on Earth, there are tens of thousands of galaxies, each with its own beach of stars. The sheer number of stars, 200 sextillion across the observable universe, immediately makes the notion of finding another Earth seem like a statistical inevitability. Surely among such an astronomical quantity, a few more Earths must exist, right? This is the initial intuitive leap that many of us make. It's the Drake equation at its most optimistic, the idea that given enough chances anything will happen. However, the challenge isn't just about the numbers of stars, vast as they are. It's about the staggering difficulty of detecting these planets, especially those that are small, rocky, and orbiting at just the right distance from their star to allow for liquid water, what we call the habitable zone. These are the specific criteria for Earth-like, and they're incredibly subtle. We're not looking for gas giants like Jupiter or scorching hot worlds orbiting their stars in mere days. We're looking for something that is, relative to its star, incredibly tiny and incredibly faint. Consider the primary methods we use to find exoplanets. The most successful by far is the watch transit method. This is where we observe a star's brightness over time, patiently waiting for a tiny, almost imperceptible dip in its light. This dip occurs when a planet passes directly in front of its star from our perspective, temporarily blocking a fraction of the star's light. Think of it like watching a distant car's headlight and noticing a momentary dimming as a fly passes across the bulb. The fly is the planet, the headlight is the star. Now, for this to work, several conditions must be met. First, the planet's orbit must be perfectly aligned with our line of sight. If the planet orbits above or below the star from our vantage point, it will never transit and will never see that telltale dip. This means that for every planet we can detect via transit, there are many, many more that are simply not aligned correctly. It's like trying to spot a fly passing a headlight from a mile away, but only if the fly happens to fly precisely between your eye and the bulb. Second, the dip in light is minuscule, especially for an Earth-sized planet. Our Sun is about 109 times wider than Earth. When Earth transits the Sun, it blocks only about 0.084% of the Sun's light. To detect such a tiny, fleeting change requires incredibly sensitive instruments, long observation times, and an absence of other stellar activity like sunspots, which can cause similar or even larger variations in brightness. These tiny signals are easily lost in the noise of a bustling star. Another common method is the radial velocity method, also known as the Doppler wobble method. This technique looks for tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. Just as a planet orbits a star, the star itself is pulled slightly by the planet, moving in a tiny reciprocal orbit around their common centre of mass. This subtle wobble can be detected by looking for shifts in the star's light spectrum, known as the Doppler effect. If the star is wobbling towards us, its light shifts slightly bluer. If it's wobbling away, it shifts slightly redder. While powerful, the radial velocity method is most effective at finding massive planets like Jupiter-sized worlds that orbit very close to their stars, because these planets exert a stronger gravitational tug and cause a more pronounced wobble. Detecting the tiny wobble caused by an Earth-sized planet orbiting in a habitable zone, which is much further out, is incredibly challenging, often pushing the limits of our current technology. The signal is simply too faint, too small, too slow. So when we say we haven't found any Earth-like planets, it's not for a lack of trying, nor necessarily for a lack of such planets existing. It's a profound statement about the limitations of our observational capabilities and the sheer difficulty of pinpointing a small rocky world that could harbour liquid water amidst the overwhelming glare of its parent star across light years of interstellar space. We are essentially trying to spot a single firefly in a hurricane from thousands of miles away, and we're only able to see it if it happens to fly directly between us and a distant lighthouse. The implications of this difficulty are vast. It means that even if Earth-like planets are common, our current methods might only be skimming the surface, detecting the easiest to find, often less Earth-like worlds. We're biased towards large planets close to their stars and perfectly aligned, This creates a kind of cosmic blind spot where the very worlds we are most interested in, the ones that truly mirror our own, are the hardest to see. It's a fundamental statistical and technological hurdle that we are still very much in the process of overcoming. So the notion that lots of stars automatically means lots of Earths is deceptively simple. The universe, in its elegant indifference, doesn't make it easy for us. The numbers are indeed vast, but the conditions for detection are incredibly restrictive, turning that cosmic lottery into a game with very specific, very hard-to-hit winning combinations. We've barely begun to scratch the surface of what's out there, and what we can detect is often just the tip of a very large, deeply hidden iceberg. This journey through the cosmic lottery has shown us that simply having billions of stars isn't enough. The universe demands a precise alignment, a delicate balance of conditions, and an almost impossible feat of observation. But what if the very definition of Earth-like itself is far more complex than just size and a habitable orbit? What if there are subtle, yet absolutely critical planetary characteristics that make a world truly habitable, characteristics that our current detection methods can't even begin to probe? In our next chapter, we'll delve into the intricate dance of planetary properties, exploring why being Earth-sized in the habitable zone is just the very first step on a long, winding road to true habitability, and how our own planet's unique characteristics might be far stranger and rarer than we ever imagined. Welcome back to Dreamy Science, where we unravel the universe's most captivating puzzles together. Last time we peered through the cosmic keyhole, discussing how our current exoplanet detection methods, the transit and radial velocity techniques, are like trying to find a specific grain of sand on every beach on Earth while blindfolded. We discovered that our observational capabilities are inherently biased, creating a vast cosmic blind spot that keeps truly Earth-like planets hidden from our view. We're really only good at spotting the big, bold, and perfectly aligned worlds, leaving the subtle, potentially life-bearing ones largely undiscovered. But here's the kicker, my friends. Even if we could magically peer into every star system and pinpoint a planet that's roughly Earth-sized and orbiting within its star's habitable zone, that sweet spot where temperatures could allow for liquid water, that's truly just the first step. It's like finding a house for sale in a nice neighbourhood and assuming it has all the plumbing, electricity, and structural integrity needed to be a home. The truth is, the conditions that make Earth a vibrant living world are far more intricate, more delicate, and frankly more miraculous than just its size and orbital distance. We're talking about a whole symphony of cosmic coincidences, a ballet of planetary characteristics that must all play in perfect harmony. Today we're going to dive deep into these astonishingly specific requirements. We'll explore the intricate planetary characteristics beyond just size and location that are absolutely critical for a world to not just exist, but to truly thrive with life as we know it. Get ready, because the more we uncover, the more unique our pale blue dot appears. First up on our cosmic checklist is a planet's atmosphere. Now you might think, oh, an atmosphere, sure, it keeps us warm. And you'd be right. But it's so much more than just a blanket. Earth's atmosphere is a complex, multi-layered shield and a vital chemical factory. It provides the pressure necessary for liquid water to exist on the surface, prevents it from boiling off into space or freezing solid. It's a breathable mixture of nitrogen and oxygen crucial for complex life. And perhaps most importantly, it acts as a planetary sunscreen, filtering out harmful ultraviolet radiation from our sun, while also trapping just enough heat to maintain a stable climate. Think of Venus, a planet roughly Earth-sized and within a similar neighbourhood in our solar system. Its runaway greenhouse effect, fueled by a thick carbon dioxide atmosphere, turned it into a scorching hellscape where lead would melt. Or Mars, with its whisper-thin atmosphere, losing heat rapidly and unable to sustain surface water. The precise composition, density, and thickness of an atmosphere are not just important, they are absolutely make or break for habitability. It's a delicate balance, a cosmic tightrope walk between too much and too little, too thick and too thin. Next, let's talk about something you can't see, but without which our atmosphere and indeed life itself would likely be stripped away: a powerful magnetic field. Earth possesses a robust magnetic field, generated by the churning molten iron in its outer core. This field extends far into space, creating an invisible shield known as the magnetosphere that deflects harmful charged particles streaming from the sun, the solar wind, away from our planet. Without it, the solar wind would slowly but surely erode our atmosphere, blowing it away layer by layer over billions of years, much like what is believed to have happened to Mars. Imagine a constant high-energy sandblasting effect on your planet. Not only does this magnetic shield protect our precious atmosphere, but it also safeguards life on the surface from dangerous cosmic radiation. To have a sustained complex biosphere, you need this planetary bodyguard working tirelessly day in and day out for eons. Then there's the subtle yet profoundly important dance happening beneath our feet: plate tectonics and geological activity. Earth isn't a static ball of rock. Its outer crust is broken into massive plates that are constantly, albeit slowly, moving, colliding and subducting. This geological activity drives the carbon silicate cycle, a natural thermostat that regulates Earth's climate over geological timescales. Volcanoes release carbon dioxide into the atmosphere, which contributes to warming, while the weathering of rocks on the surface removes CO2, leading to cooling. This dynamic interplay prevents Earth from either freezing solid or spiraling into a runaway greenhouse effect. Plate tectonics also recycles nutrients, forms continents, and creates diverse habitats. Without this internal engine, a planet might become a geologically dead world, unable to regulate its climate or replenish geoelements necessary for life. It's Earth's internal life support system, constantly churning and renewing. And what about the very essence of life itself as far as we understand it? Liquid water. We've established that the habitable zone is where water could be liquid, but that's a big could. A planet needs to actually have water in the first place and then maintain it in its liquid state. Did the water arrive via icy comets, or outgas from the planet's interior? Once there, can the planet hold on to it? Too much atmospheric escape can lead to a dry, barren world. Too little internal heat, and it might freeze solid from the surface to the core. And here's another thought. What if a planet is entirely covered in water, a water world? While seemingly ideal, a deep global ocean might prevent the necessary chemical interactions between water, atmosphere, and rock that are thought to be crucial for the origin and diversification of life. It's not just about having water, it's about having the right amount of water, distributed in the right way, interacting with the right kind of geology. Now let's look up at our night sky and acknowledge our silent, steadfast companion. The moon. Earth's moon is unusually large relative to its parent planet, and this is another critical piece of our planetary puzzle. Our moon acts as a gravitational anchor, stabilizing Earth's axial tilt. Without it, Earth's tilt would likely wobble wildly over millions of years, leading to extreme chaotic climate swings that would make the sustained evolution of complex life incredibly challenging, if not impossible. Imagine ice ages and scorching deserts alternating with unpredictable ferocity. The moon also generates our tides, which some theories suggest played a vital role in the early chemistry of life, providing dynamic intertidal zones where complex molecules could form and interact. It's more than just a beautiful celestial body. It's a cosmic dance partner that ensures our planet's long-term stability. Then there's the star itself, our host star characteristics. Our Sun is a G-type yellow dwarf, a relatively stable star, with a long lifespan of about 10 billion years. This extended period of stable energy output has provided billions of years for life to emerge, evolve, and diversify. But what about other stars? The most common stars in our galaxy are red dwarfs, M-type stars. While they also have incredibly long lifespans, planets in their habitable zones would have to orbit extremely close to receive enough warmth. This proximity often leads to tidal locking, meaning one side of the planet is perpetually scorched and the other perpetually frozen. Red dwarfs are also prone to powerful, frequent flares that could easily strip away atmospheres or sterilize a planet's surface. On the other end of the spectrum, massive O and B-type stars burn incredibly hot and bright, but their lifespans are tragically short, lasting only a few million to tens of millions of years. Hardly enough time for complex life to even begin its journey. So not just any star will do. We need a star with the right temperament and longevity. Finally, consider the larger cosmic neighborhood. The orbital stability and architecture of the entire planetary system. Our solar system is remarkably stable, with planets orbiting in nearly circular paths, largely thanks to the gravitational influence of Jupiter. Our gas giant acts like a cosmic big brother, clearing out potentially devastating asteroids and comets from the inner solar system, protecting Earth from a barrage of impacts. Many exoplanetary systems we've discovered, however, are far more chaotic. We've found hot Jupiters orbiting incredibly close to their stars, or systems with planets in highly eccentric elongated orbits that would create extreme temperature fluctuations and gravitational perturbations, likely making any inner, potentially habitable planets unstable. The careful arrangement of planets, the presence of a sweep-up giant like Jupiter, and the overall long-term gravitational stability are all crucial, intricate parts of the habitability equation. So as you can see, finding an Earth-sized planet in a habitable zone is truly just the very first whisper in a symphony of requirements. We're not just looking for a house, we're looking for a house with the perfect climate control, a built-in force field, a self-regulating foundation, the ideal water supply, a giant stabilizing moon, a gentle and long-lived landlord, and a well-behaved neighborhood. The sheer number of these Goldilocks conditions that must all align perfectly, simultaneously, and for billions of years is mind-boggling. It makes you wonder, doesn't it? Are we truly alone in our cosmic island? Or are we simply peering through a pinhole at a universe teeming with life, yet perfectly hidden from our limited view? And what if, even with all these conditions met, there's another, even more profound layer to this mystery? What if the timing of life's emergence, or the very definition of life itself, is another variable we haven't even begun to fully grasp? Join us next time on Dreamy Science as we continue our journey into the profound questions of existence, and perhaps uncover even more reasons why finding another Earth might just be the greatest cosmic treasure hunt of all. Welcome back to Dreamy Science, my friends, where we're peeling back the layers of cosmic mystery, one star system at a time. Last time we dove deep into the mind-boggling array of Goldilocks conditions that make our Earth not just a comfortable home, but a truly miraculous one. We talked about everything from a planet's magnetic field and plate tectonics to the stabilizing influence of a large moon and the perfect temperament of its host star. We even touched upon the cosmic bouncer role of a gas giant like Jupiter. The sheer number of these precise simultaneous conditions, all needing to align just so, makes our blue marble seem remarkably unique, doesn't it? It's enough to make you wonder, are we truly alone? Is life common but perfectly hidden? Or are we perhaps looking for life in all the wrong places, or even defining it too narrowly? Today we're going to grapple with these profound questions, pushing beyond the mechanics of detection and the laundry list of planetary features, to explore the deeper, more philosophical reasons why finding another Earth remains such an elusive dream. Think of it this way. Imagine you're trying to win a cosmic lottery. In Chapter 1, we learn that just detecting a ticket, a planet, is incredibly hard. Our methods are biased, and the universe is vast. In Chapter 2, we discover that even if you find a ticket, it's not enough for it to simply exist. It has to be the winning ticket, with all the right numbers perfectly aligned. Now in Chapter 3, we're asking, what are the odds of all those winning numbers coming up simultaneously, and then persisting for long enough to matter? Let's do some quick arithmetic, not with numbers, but with probabilities. If the probability of an Earth-sized planet in a habitable zone is, say, 1 in 1,000, and the probability of it having a strong magnetic field is another 1 in 1,000, and the probability of plate tectonics, and a large moon, and the right atmospheric composition, and a stable star, and a Jupiter-like protector, you see where this is going, don't you? Each additional Goldilocks factor, while perhaps not individually rare, multiplies the improbability of them all converging. It's like needing to roll a 6 on a 100-sided die, then another 6 on a different 100-sided die, and another, for dozens of consecutive rolls. The odds quickly become astronomically small. This compounding improbability is at the heart of what's often called the rare Earth hypothesis. It suggests that while simple microbial life might be common throughout the universe, the emergence of complex multicellular life, the kind of life that could eventually build telescopes and wonder about its cosmic neighbours, requires such a precise, interlocking set of geophysical and astronomical circumstances that it might indeed be exceedingly rare. Our Earth, in this view, isn't just a lucky planet, it's a cosmic anomaly, a jewel forged in a crucible of improbable perfection. But even if all these conditions do align, there's another critical ingredient we haven't fully explored: time. It's not enough for a planet to have all the right features for a fleeting moment. Life, particularly complex life, needs billions of years to emerge, evolve, and diversify. Our own Earth took roughly 3.5 billion years for the first multicellular organisms to appear, and another 500 million for complex life to truly flourish. That's a long cosmic clock. So what does this mean for our search? It means we need a star that's stable and long-lived, like our Sun, which has shone steadily for 4.5 billion years, and has another 5 billion to go. It means the planet's conditions must remain stable over eons, not just millennia. Imagine a planet that develops a perfect atmosphere, but then its star goes through a volatile phase stripping it away, or a planet with liquid water, but its plate tectonics grind to a halt, ending the carbon cycle and throwing its climate into chaos. The universe is dynamic, often violent, and incredibly impatient. A planet needs not just the right conditions, but the endurance to maintain them against cosmic assaults, solar fluctuations, and internal geological shifts for billions of years. This long-term stability is yet another layer in our cosmic treasure hunt. And this brings us to another profound challenge. the detectability of life itself. Even if a planet does harbour life, what are we looking for? We're often searching for biosignatures, chemical compounds in a planet's atmosphere that are strongly indicative of biological processes like oxygen, methane, or ozone. On Earth, the massive amounts of oxygen in our atmosphere are a screaming billboard for life. But what if alien life doesn't produce these specific gases? What if it's based on entirely different biochemistry? What if it's microbial, hidden deep underground or beneath oceans, and doesn't significantly alter its planet's atmosphere in ways we can detect from light years away? Our current search criteria are, understandably, somewhat Earth-centric. We look for water, for temperatures conducive to carbon-based life, for atmospheres that might sustain us. But the universe is a canvas of infinite possibilities. What if life can thrive in conditions we consider utterly hostile? What if there are forms of life so alien, so fundamentally different from anything we know, that their biosignatures are completely foreign to our instruments and our understanding? The very definition of life itself, when stretched across the cosmos, becomes a blurry, enigmatic concept. We might be staring right at it and simply not recognize it. And let's not forget our own cosmic address. Our solar system isn't just a random speck in the Milky Way. It occupies a rather privileged position. We're nestled in a quiet, stable region, far enough from the chaotic, radiation-soaked galactic centre, where supermassive black holes and frequent supernovae make for a rather inhospitable neighbourhood. Yet, we're not so far out in the galactic boondocks that we lack the heavier elements, the metals in astronomical parlance necessary to form rocky planets and the building blocks of life. This is what astronomers call the galactic habitable zone. A specific region within a galaxy where conditions are just right for life to emerge and thrive. It's another Goldilocks zone, but on a truly colossal scale, adding yet another filter to our search. So when we combine the statistical improbability of all the Goldilocks conditions aligning with the necessity of these conditions persisting for billions of years, and then factor in the limitations of our current detection methods and our potentially narrow definition of life, the picture becomes incredibly complex. We're not just looking for a needle in a haystack. We're looking for a specific microscopic piece of straw which might not even be straw in a haystack the size of a galaxy, and we only have a pair of tweezers and a magnifying glass. Does this mean we are alone? Perhaps. Or perhaps it means the universe is so vast, so intricate, and so utterly beyond our current comprehension that our search has only just begun. The journey of dreamy science is one of humility in the face of such cosmic grandeur, but also one of boundless curiosity. With every new telescope, every new theoretical model, every new detection method, we're refining our understanding, expanding our reach, and pushing the boundaries of what's possible. The universe isn't just a collection of stars and planets, it's a grand, evolving story, and we are privileged to be a part of its unfolding. The fact that we haven't yet found another Earth-like planet isn't a failure. It's a testament to the profound uniqueness of our own existence, and a challenge to look harder, think deeper, and dream bigger. Next time on Dreamy Science, we'll delve into the exciting frontiers of exoplanet research, exploring the innovative technologies and groundbreaking missions that are pushing the boundaries of our search, and perhaps finally bringing us closer to answering that most fundamental question: are we truly alone? Until then, keep looking up, keep wondering, and keep dreaming. Welcome back, cosmic explorers, to Dreamy Science. We've embarked on quite the journey together, haven't we? From the mind-boggling scale of the universe to the incredibly specific, almost miraculous symphony of conditions that allow our own planet to thrive. we've grappled with the profound implications of the rare Earth hypothesis, considering just how astronomically improbable it might be for all those Goldilocks factors to align perfectly, not just for simple microbial life, but for the complex multicellular ecosystems we see flourishing around us. And we've acknowledged the immense challenge of even detecting such life, given our Earth-centric definitions and the vast cosmic distances. So where do we go from here? Does this compounding improbability, this cosmic silence, mean we should simply throw up our hands and declare Earth a singular lonely marvel? Absolutely not. For every unanswered question in science, there is an invitation, an irresistible pull to innovate, to explore, to push the boundaries of what's possible. The mystery isn't a dead end, it's a wide-open highway beckoning us forward. Today, we're going to turn our gaze towards that future. We're going to explore the cutting-edge tools and ambitious missions that humanity is developing or dreaming of to pierce through the cosmic veil. We'll delve into how we're refining our search, broadening our definitions, and attempting to overcome the very limitations we've discussed. This isn't just about finding another Earth. It's about understanding the universe itself, and perhaps our own unique place within it. Think back to those early days of exoplanet hunting, when we were essentially trying to spot a firefly's shadow in a hurricane using a telescope designed for static stars. Our initial methods, the transit and radial velocity techniques, were groundbreaking, but inherently biased towards large planets orbiting close to their stars. They were like casting a fishing net with enormous holes. We caught the biggest fish, but countless smaller, perhaps more interesting specimens slipped right through. Now imagine that net getting finer, more sensitive, capable of detecting the most subtle disturbances. That's the trajectory of our current and future astronomical endeavours. One of the most revolutionary instruments currently reshaping our understanding of the universe is the James Webb Space Telescope, or JWST. You've seen its breathtaking images, I'm sure. Galaxies born in the dawn of time, stellar nurseries glowing with nascent suns. But for exoplanet research, JWST is nothing short of a game changer, particularly in its ability to characterize exoplanet atmospheres. How does it do this? Remember the transit method. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching our telescopes. JWST, with its incredible infrared sensitivity, can analyze that filtered light. Different molecules in the atmosphere, like water vapor, carbon dioxide, methane, or oxygen, absorb specific wavelengths of light. By looking for these sectoral fingerprints, JWST can begin to tell us what an exoplanet's atmosphere is made of. This isn't just about finding any atmosphere, it's about searching for biosignatures. These are chemical compounds or combinations of compounds that, on Earth, are strongly indicative of life. For instance, a significant amount of oxygen in an atmosphere that isn't being produced by the geological processes, combined with methane, could be a strong hint. Why? Because oxygen and methane react with each other. Their simultaneous presence suggests something is actively replenishing them, and on Earth, that something is life. But here's the rub, and it brings us back to the complexity we discussed. Even with JWST, we're still largely limited to observing planets transiting bright, relatively close stars. And interpreting those spectral fingerprints is incredibly difficult. A planet might have oxygen, but is it from life or from a runaway greenhouse effect boiling off oceans and breaking water molecules apart? It's like trying to diagnose a complex illness based on a single faint symptom. We need multiple lines of evidence, a whole symphony of biosignatures, to even begin to make a compelling case. And even then, We might be blindsided by an alien biochemistry we haven't even conceived of. This is why the scientific community is already dreaming bigger, much bigger. Beyond JWST, there are ambitious concepts for future observatories, often referred to as flagship missions. Think about missions like the Habitable Worlds Observatory HWO, or its predecessors, concepts like R, Large Ultraviolet Optical Infrared Surveyor, and HabEx, Habitable Exoplanet Imaging Mission. These are not just incremental improvements, they represent a generational leap in our capabilities. These future telescopes are designed to do something truly extraordinary. Direct imaging of Earth-sized exoplanets. Instead of just seeing the subtle dimming of a star, they aim to actually see the planet itself as a tiny, faint speck of light separate from its star. Imagine trying to spot a firefly next to a lighthouse from hundreds of miles away, and then trying to analyze the color of the firefly's glow. That's the challenge. To achieve this, these telescopes would employ sophisticated technologies like starshades, massive flower-shaped spacecraft that would fly tens of thousands of miles in front of the telescope, precisely blocking out the blinding light of the host star. With the star's glare suppressed, the faint reflected light from an orbiting exoplanet could finally be resolved. What would direct imaging allow us to do? It would open up a whole new realm of atmospheric characterization. We could get much clearer, more detailed spectra, allowing us to search for a wider range of biosignatures and perhaps even signs of surface features like oceans or continents. We could observe planets that don't transit their stars, dramatically expanding our search space beyond the narrow slice of the sky accessible to JWST's transit spectroscopy. But here's the kicker. Even with these phenomenal future instruments, the sheer scale of the universe remains our most formidable adversary. There are billions upon billions of stars in our galaxy alone. Even if these future telescopes could analyze the atmospheres of hundreds or even thousands of potentially habitable planets, that's still an infinitesimally small fraction of the total. It would be like sampling a handful of grains of sand from all the beaches on Earth and expecting to find a specific uniquely coloured grain. Moreover, our definition of Earth-like and life itself is evolving. We've focused heavily on the Goldilocks zone, the region around a star where liquid water could exist on a planet's surface. But what if life doesn't need to be on the surface? What about the subsurface oceans of icy moons like Europa or Enceladus in our own solar system? These worlds, far beyond the traditional habitable zone, show tantalizing signs of hydrothermal vents and liquid water, potentially harboring life completely independent of sunlight. Our search for biosignatures might need to expand beyond atmospheric gases to include geochemical clues from cryovolcanism or even direct sampling by future probes. And what if life isn't carbon-based or doesn't use water as a solvent? While the fundamental principles of chemistry and thermodynamics suggest carbon and water are exceptionally well suited for complex biochemistry, the universe is vast enough to challenge our assumptions. We are, after all, looking for something based on the only example we have: us. This inherent anthropocentrism in our search could be a profound blind spot. Then there's the question of techno-signatures. What if advanced alien civilizations exist but they don't produce biosignatures we can detect? Perhaps they've mastered their environments, or moved underground, or left their home planets entirely. The search for technosignatures, signs of technology like radio signals, artificial structures, or even industrial pollution, is a different yet parallel quest. Projects like SETI, Search for Extraterrestrial Intelligence, have been listening for decades, and while the silence has been profound, the search continues, employing ever more sophisticated algorithms and observing methods. So as we look to the future, we face a multi-layered challenge. We need instruments powerful enough to detect incredibly faint signals across unimaginable distances. We need to refine our understanding of what constitutes life and its signatures, moving beyond our Earth-centric biases. And we need to grapple with the sheer, overwhelming numbers, the cosmic lottery of chance, combined with the vastness of space and time. The silence we've encountered so far isn't necessarily a sign of cosmic emptiness. It's a testament to the immense difficulties of the search itself. It reminds us that our tools are still nascent, our understanding still incomplete, and our perspective still limited. But in this challenge lies the greatest adventure. The quest to find another Earth, or any form of life beyond our own, forces us to look inward as much as outward. It compels us to understand the intricate dance of physics, chemistry, and biology that allowed us to come into being. Ultimately, the ongoing quest, the development of these incredible future telescopes and methods, deepen our appreciation for our own planet. Each new challenge, each refinement in our search, underscores the profound uniqueness and preciousness of Earth. It is a cosmic island teeming with life, a vibrant anomaly in a seemingly vast and empty ocean. And our journey, our shared exploration through dreamy science, has only just begun to truly understand why. Next time we'll delve even deeper, considering the philosophical implications of this profound search and what it truly means for humanity to be alone or not in the grand tapestry of the cosmos. Until then, keep looking up, keep wondering, and keep dreaming. Welcome back to Dreamy Science, where our cosmic journey continues to unravel some of the universe's most profound mysteries. We've delved deep into the intricate dance of planetary formation, the precise Goldilocks conditions that make Earth a veritable miracle, and the technological marvels we're deploying to peer further into the cosmic abyss. We've even considered the mind-bending possibility that life, as we know it, might be far rarer than our initial hopes suggested. But now it's time to confront perhaps the most unsettling silence in the universe. Where is everybody? This isn't just a philosophical musing. It's a scientific conundrum known as the Fermi paradox. Enrico Fermi, the brilliant physicist, famously posed this question in 1950 during a casual lunch conversation. Given the sheer scale of the universe, billions upon billions of stars, many of them billions of years older than our Sun, and the statistical likelihood that some fraction of these stars should host planets capable of developing intelligent life, then where are the signs? Where are the galactic empires, the probes, the radio signals, the cosmic postcards? If life, even intelligent life, is common, then the universe should be teeming with it. Civilization should have had ample time to spread, to colonize their galaxies, or at least to leave an unmistakable technological footprint. Yet, as we listen with our most sensitive instruments, as we scan the skies with our most powerful telescopes, we are met with an echoing, profound silence. This silence, my friends, is not just a lack of data. It's a data point in itself. It forces us to confront some truly humbling and at times terrifying possibilities. Let's explore some of the most compelling proposed solutions to the Fermi paradox, many of which directly build upon the concepts we've explored in previous chapters. One of the most immediate and impactful solutions is the rare Earth hypothesis, which we discussed at length in Chapter 3. This hypothesis posits that while simple microbial life might be common across the cosmos, the specific, intricate and stable conditions required for the emergence and sustained evolution of complex, multicellular intelligent life are incredibly rare. Remember our litany of Goldilocks conditions: the stable star, the perfect planetary orbit, the right-size moon, plate tectonics, a magnetic field, a Jupiter-like protector, a stable galactic neighborhood, and all of these factors persisting for billions of years. If even one of these critical parameters is slightly off, the evolutionary ladder might never get beyond the microbial rung, or perhaps it collapses before intelligence can emerge. If this hypothesis holds true, then Earth isn't just a planet, it's a cosmic island, a unique sanctuary where an astonishing confluence of favourable circumstances has allowed life to flourish and evolve into self-aware beings capable of contemplating our own existence. The silence in this scenario isn't eerie. It's simply a reflection of an incredibly sparse cosmic neighbourhood when it comes to intelligent company. We might be, if not entirely alone, then separated by such immense distances that communication becomes practically impossible. But what if the problem isn't the rarity of life, but something more sinister? This brings us to the chilling concept of the Great Filter. This idea suggests that somewhere between the emergence of simple life and the development of a galaxy-spanning civilization, there exists a filter, a monumental hurdle or catastrophe that almost all life forms fail to overcome. The Great Filter could be in our past, meaning humanity has already passed it. Perhaps the emergence of life itself is incredibly improbable, or the leap from single-cell to multicellular organisms, or from simple animals to intelligent tool users is the filter. If so, then we are incredibly lucky and perhaps the first, or among the very few, to have made it this far. This would make our existence even more precious, but also perhaps more lonely. More unsettlingly, the Great Filter could be in our future. This is the scenario that keeps many scientists and thinkers awake at night. What if civilizations inevitably develop the means to destroy themselves? Through nuclear war, runaway climate change, engineered pandemics, or uncontrolled artificial intelligence, before they can achieve interstellar travel? Or what if there's a naturally occurring cosmic event, like a gamma-ray burst or an asteroid impact, that is simply too frequent for civilizations to outrun? The silence in this context would be a grim warning, a graveyard of civilizations that never made it past a certain technological or evolutionary threshold. It would mean that our current challenges, climate change, global conflicts, the responsible development of powerful new technologies, aren't just terrestrial problems, they are potentially universal filters. Then there's the possibility that we are simply not looking in the right way, or that advanced civilizations have no interest in communicating with us. This is where our detection challenges, which we explored in Chapter 1 and Chapter 4, come back into play. Our methods are still rudimentary, biased towards certain types of planets and certain types of signals. What if alien civilizations communicate using methods we haven't even conceived of yet? Perhaps they transmit information through neutrinos, or gravitational waves, or some other quantum entanglement we can't detect. We're essentially trying to catch a whisper in a hurricane with a tin can and string, while the whisper might be a symphony played on instruments we can't even imagine. Consider the zoo hypothesis. Perhaps advanced civilizations are aware of us, but they choose not to interfere, treating Earth as a kind of protected nature reserve or a laboratory experiment. They might have a prime directive, much like in science fiction, to observe without interaction until we reach a certain level of maturity or technological advancement. Or perhaps they simply find us uninteresting, a nascent civilization too primitive to warrant their attention. It's a humbling thought, isn't it? To be the cosmic equivalent of an ant farm. And what about the yet dark forest hypothesis? This is a much darker take, suggesting that the universe is a dangerous place. Any civilization that announces its presence broadcasts its location and resources to potential predators. Therefore, the safest strategy is silence. Every civilization is constantly listening but never broadcasting out of fear of attracting unwanted attention. If this is true, the cosmic silence isn't empty. It's filled with hidden eyes and silent listeners, each terrified of being the first to break the quiet. Finally, we must consider the possibility that alien life, especially intelligent alien life, is simply too alien for us to recognize. Our search for biosignatures and technosignatures is inherently anthropocentric. We look for oxygen, methane, water, radio waves, all things that resonate with our own biological and technological evolution. But what if life can arise and thrive in conditions we deem impossible? What if intelligence manifests in ways utterly foreign to our carbon-based bipedal brains? Could there be silicon-based life or energy beings or intelligences that exist within the fabric of space-time itself? Could their technology be indistinguishable from natural phenomena to our current instruments? This possibility underscores the importance of broadening our definitions of life and intelligence, as we touched upon in Chapter 4, pushing the boundaries of our imagination. So where does this leave us? The Fermi paradox isn't just a puzzle, it's a mirror. It reflects our own biases, our technological limitations, and our profound uncertainty about our place in the cosmos. The answers, if they ever come, will fundamentally reshape our understanding of ourselves and the universe. The silence could mean we are incredibly rare, a precious and unique gem in a vast empty ocean. If so, it places an immense responsibility upon us to cherish and protect our home, this fragile blue marble, and to ensure our own survival. The search then becomes less about finding others and more about understanding the miracle of our own existence. Or the silence could be a warning, a cosmic echo of the challenges that lie ahead for any developing civilization. If so, it's a powerful call to action, urging us to overcome our divisions, to steward our planet wisely, and to navigate our technological advancements with profound caution. Or perhaps the universe is teeming with life, but we are simply not yet equipped to perceive it, or we haven't yet earned the right to join the cosmic conversation. Our journey to find answers is a testament not only to our scientific ingenuity, but also to our enduring curiosity, our boundless hope, and our fundamental need to connect. The search for Earth-like planets, for biosignatures, for technosignatures, and for answers to the Fermi paradox isn't just about distant stars and alien worlds. It's about understanding the very nature of life, intelligence, and our own destiny. It's about peering into the vast unknown and realizing that the most extraordinary discovery we might ever make is the profound uniqueness of our own existence right here, right now on this incredible planet we call home. The questions remain, vast and echoing, but our pursuit of the answers continues, fueled by wonder, humility, and an unshakable dream. Welcome back, cosmic explorers, to Dreamy Science. In our last chapter, we grappled with the profound silence of the universe, diving headfirst into the myriad explanations for the Fermi paradox. We considered everything from the chilling possibility of a great filter to the idea that alien life might simply be too alien for us to recognize, or perhaps even too wise to reveal itself. Each proposed solution in its own way casts a long, thought-provoking shadow across our understanding of life's prevalence in the cosmos. But as we ponder these vast philosophical answers, I find myself drawn back to a more immediate, tangible question. What if the filter isn't some grand cosmic event out there, but rather an incredibly precise, almost miraculous set of circumstances that allowed life, and specifically complex, intelligent life, to flourish right here on Earth? What if the very fabric of our planet, from its molten core to its shimmering atmosphere, represents a convergence of conditions so improbable that finding an exact twin becomes less like finding a needle in a haystack and more like finding a specific grain of sand, perfectly shaped and coloured, on every single beach across an entire continent? Today we're going to delve deeper into the astonishing uniqueness of Earth itself. We've talked about the Goldilocks zone, that perfect orbital distance from a star where temperatures allow for liquid water. But as you're listening, I want you to imagine that Goldilocks isn't just about temperature. It's about a symphony of cosmic coincidences, a planetary ballet where every single dancer, from the smallest atom to the largest geological force, performs its part with exquisite precision over billions of years. Think about it. What does it truly mean to be Earth-like? Is it simply a rocky planet of similar size, orbiting in a habitable zone? Our current exoplanet surveys, as we discussed, are doing an incredible job of identifying such worlds. But the more we learn about our own planet, the more we realize that Earth-like is a far more demanding descriptor than we ever imagined. It's not just about the address. It's about the entire cosmic neighbourhood, the house's foundation, its plumbing, its heating system, and even the air conditioning. Let's start with Earth's molten heart. Deep beneath our feet lies a churning liquid iron outer core, surrounding a solid iron inner core. This colossal dynamo, driven by the planet's rotation and internal heat, generates Earth's powerful magnetic field, our planetary shield. This magnetosphere deflects harmful solar winds and cosmic radiation, preventing them from stripping away our atmosphere and sterilizing the surface. Without it, our planet would likely resemble Mars, a cold, dry, irradiated wasteland. But how rare is such a robust, long-lasting magnetic field? It requires a specific planetary size, composition, and internal heat engine to sustain for billions of years. Many planets might form, but how many maintain this crucial protection for the duration needed for complex life to evolve? We don't know because we can't detect a magnetic field from light years away. It's an invisible yet utterly essential prerequisite for prolonged habitability. Then there are plate tectonics. This geological ballet, where continents drift, collide, and subduct, isn't just responsible for mountains and earthquakes. It's a fundamental component of Earth's long-term climate regulation, specifically the carbon silicate cycle. Volcanic activity releases carbon dioxide into the atmosphere, while the weathering of rock sequesters it. Plate tectonics ensures a continuous exchange, preventing runaway greenhouse effects like Venus, or global ice ages like Mars. It also recycles nutrients, bringing fresh minerals to the surface, and helps regulate our planet's internal temperature. For life, it's a colossal slow-motion thermostat. But what enables plate tectonics? It's thought to require a specific planetary size, a certain amount of internal heat, and crucially the presence of liquid water within the mantle to lubricate the plates. Take away any one of these ingredients, and you might end up with a stagnant lid planet, where the crust remains a single unbroken shell, effectively halting this vital cycle. How many exoplanets have active long-lived plate tectonics? Again, we have no way of knowing from our current observational techniques. And what about our moon? Earth's moon is an anomaly. It's unusually large relative to its host planet, and its formation via a colossal impact with a Mars-sized protoplanet early in Earth's history was a truly cataclysmic yet ultimately beneficial event. This massive moon stabilizes Earth's axial tilt, preventing wild, chaotic swings in our planet's orientation that would lead to extreme climate variations, potentially making the long-term evolution of complex life impossible. It also generates tides, which may have played a critical role in the emergence of life from primordial oceans, creating dynamic intertidal zones where complex chemistry could unfold. How many planets have such a perfectly sized, perfectly placed, stabilizing lunar companion? The physics of such a large impact and the subsequent orbital stability suggest it's not a common occurrence. It's like winning the cosmic lottery for planetary formation. Let's not forget the very stuff of life: water. We know liquid water is essential, but how Earth got its vast oceans is still debated. Was it delivered by comets and asteroids? Did it outgas from the planet's interior? Whatever the mechanism, Earth received the perfect amount, enough to cover most of its surface, but not so much that it would form a global ocean hundreds of miles deep, preventing the necessary land-sea interfaces and plate tectonics. It's a delicate balance, a cosmic sweet spot. Even our Sun, a seemingly ordinary G-type star, turns out to be remarkably stable. It doesn't flare violently like some M-dwarfs, which could sterilize nearby planets, nor does it have extreme luminosity variations. Its long, stable lifespan of billions of years has provided the consistent energy input necessary for life to emerge and evolve from simple single-celled organisms to complex, intelligent beings. And our position in the Milky Way, within the galactic habitable zone, away from the chaotic, radiation-soaked galactic core, yet with enough heavy elements for planet formation, further refines this cosmic address. When we consider all these factors, the robust magnetic field, the active plate tectonics, the stabilizing giant moon, the perfect amount of water, the stable star, the favorable galactic neighborhood, we begin to see that Earth-like isn't just a broad category. It's a highly specific, multi-layered set of conditions that must not only exist but also persist for billions of years. It's like trying to find a perfectly functioning antique clock where every single gear, spring, and jewel is original, in perfect working order, and has been ticking flawlessly for millennia. This realization doesn't diminish our search for exoplanets. It deepens our appreciation for Earth's profound uniqueness and underscores the immense challenge of finding a true twin. When we say we've found a potentially habitable exoplanet, what we usually mean is that it's a rocky world in the habitable zone of its star. But this is just the first, most superficial layer of habitability. It tells us nothing about its magnetic field, its geological activity, its moon system, or the exact composition and evolution of its atmosphere over cosmic timescales. So, the Great Filter might not be a single event, but rather a series of incredibly tight interwoven filters that a planet must pass through, not just once but continuously for billions of years. Each of these planetary conditions, from the iron core to the stable axial tilt, represents a separate low-probability hurdle, and the probability of all of them aligning perfectly and remaining stable for the unfathomable duration required for complex multicellular life to arise and evolve into intelligence. That, my friends, is the truly mind-boggling arithmetic we're up against. This isn't to say that other forms of life don't exist, or that they won't be found on planets that don't perfectly mirror Earth. Life, as we know, is tenacious and adaptable. But when we talk about finding another Earth-like planet, A world capable of fostering complex technological civilizations similar to our own. We're asking for something profoundly specific. We're asking for a planet that has won the cosmic lottery not just once, but countless times, across billions of years. Our current telescopes, as powerful as they are essentially looking for the address and perhaps a rough sketch of the house. They can tell us if it's rocky, how big it is, and if it's in the right neighbourhood. But they can't tell us if the foundation is stable, if the plumbing works, if the air is breathable, or if there's a complex, self-regulating ecosystem thriving within. We are, in essence, looking for the visible tip of an unimaginably vast and complex iceberg. As we move forward, our understanding of Earth's unique conditions will continue to inform and refine our search for exoplanets. We'll develop new instruments and techniques to probe deeper, to look for those subtle biosignatures and technosignatures that might hint at these underlying planetary mechanisms. But for now, the more we learn about our own precious home, the more we realize just how extraordinary it truly is. It makes you wonder, doesn't it? If Earth is such a cosmic marvel, an improbable convergence of so many fortunate events, then perhaps the silence isn't so mysterious after all. Perhaps we are, for now, a truly rare jewel in the cosmic crown. In our next chapter, we'll shift our gaze from the planetary to the biological. We'll explore the incredible journey of life itself on Earth, the vast timescales, the evolutionary bottlenecks, and the sheer improbability of intelligence arising from the primordial soup. What if the great filter isn't just about forming the right planet, but about the specific tortuous path that life must take to reach self-awareness? Join me then as we continue our dreamy science exploration into the most profound questions of our existence. Until next time, keep looking up and keep wondering. Welcome back to Dreamy Science, my fellow cosmic adventurers. As you've journeyed with me through the intricate dance of planetary formation, the Goldilocks conditions, and the mind-boggling scale of the universe, we've found ourselves staring into the profound abyss of a truly baffling question. If the cosmos is so vast, teeming with billions upon billions of galaxies, each home to billions upon billions of stars, many of which likely host planets, then where is everybody? This, of course, is the heart of the Fermi paradox, the cosmic silence that whispers not of absence, but of an enigma. We've explored the astronomical unlikelihood of Earth's precise conditions, the limitations of our current detection methods, and the vast distances that make even our closest stellar neighbours feel like unreachable islands. But what if the silence isn't just about rarity or distance? What if it's a message in itself, a warning, or perhaps even a deliberate choice? Today we're going to delve deeper into the most chilling and thought-provoking explanations for this silence, concepts that challenge our assumptions about life in the universe and force us to confront our own place within it. We're talking about the Great Filter, the zoo hypothesis, and the unnerving dark forest. Let's begin with the Great Filter. Imagine, if you will, the journey of life from its simplest microbial beginnings to a complex, intelligent, spacefaring civilization. This journey isn't a smooth open highway, it's an obstacle course fraught with monumental hurdles. The Great Filter is precisely that, a critical evolutionary or technological barrier that is incredibly difficult for life to overcome. It's a stage in the development of life that is so improbable, so challenging, that very few, if any, civilizations ever make it past it. The chilling question then is this: is the Great Filter behind us, or is it still ahead? If the Great Filter is behind us, it means that the incredible rarity of intelligent, complex life isn't due to a lack of stars or planets, but because the path to get here, to us, was astonishingly improbable. In this scenario, we, humanity are the lucky ones. We've already passed the cosmic bottleneck that has snuffed out countless potential life forms or prevented them from ever reaching our level of development. Think back to everything we've discussed: the precise amount of liquid water, the magnetic field, plate tectonics, a stable planetary system with a Jupiter-like protector, a large stabilizing moon, a long-lived star, and a safe galactic neighborhood. Each of these on its own is a Goldilocks condition, but for all of them to align and then to persist for billions of years, allowing for the slow, meandering and often chaotic process of evolution to culminate in multicellular organisms, then complex life, and finally self-aware, tool-using, stargazing beings like us. That, my friends, is a truly mind-boggling series of improbable events. Consider the sheer unlikeliness of abiogenesis itself, the initial spark of life from non-living matter. We still don't fully understand how that happened on Earth. Was it a freak accident, a statistical anomaly that rarely, if ever, repeats elsewhere? And even if life does spark, what about the transition from simple prokaryotes to complex eukaryotes with their intricate internal structures? That was a monumental leap, taking billions of years on Earth. Then the development of multicellularity, sexual reproduction, consciousness, language, tool use, and finally the scientific method and space travel. Each step is a potential filter, a hurdle so high that almost no one makes the jump. If this is the case, if the great filter is indeed in our past, then the cosmic silence isn't a sign of danger, but a profound testament to our own astonishing uniqueness. It means we might be, if not alone, then among an incredibly select few, a cosmic lottery winner against unfathomable odds. It transforms the vast, empty universe from a potential playground of civilizations into a lonely, silent expanse where life, especially complex life, is an almost miraculous exception. This perspective, while humbling, also imbues our existence with an immense, almost unbearable preciousness. But what if the great filter is ahead of us? This is where the implications become truly chilling. If countless civilizations do arise across the galaxy, but none of them ever reach the stage of interstellar travel or long-term survival, it implies that there's a catastrophic hurdle that almost universally wipes them out. And if that's true, then we, humanity, might be rapidly approaching it. What could such a future great filter look like? The possibilities are vast and terrifying. We could be talking about existential threats that are either self-inflicted or purely external. On the self-inflicted side, imagine a civilization developing advanced technology but failing to manage its consequences. Climate change, for instance, could render a planet uninhabitable long before its inhabitants develop interstellar capabilities. Nuclear war, a spectre that has haunted humanity for decades, could easily trigger a planetary collapse. What about runaway artificial intelligence, developing beyond our control and deciding humanity is a threat or simply irrelevant? Or novel biological weapons, pandemics of unprecedented lethality, or even unforeseen consequences of advanced physics experiments? The very tools that grant us power and progress could, if misused or misunderstood, become our undoing. Then there are the external cosmic threats. We've been incredibly lucky so far. A sufficiently large asteroid or comet impact could cause an extinction-level event. Supervolcano eruptions, though rare, could trigger global climate catastrophe. A nearby supernova or a powerful gamma-ray burst could sterilize a planet's surface, stripping away its atmosphere or bathing it in lethal radiation. While our solar system has a galactic sweet spot, even there, cosmic dangers lurk. The universe, in its grandeur, is also a place of immense, impersonal violence. The implications of a future great filter are profoundly sobering. Every radio signal we send out, every technological leap we make, every step toward unraveling the universe's mysteries could be bringing us closer to a precipice. The cosmic silence in this context isn't just empty, it's a warning, a tombstone for all who came before, a silent testament to the universal, inescapable fate of intelligent life. It suggests that perhaps the most dangerous time for any civilization is precisely when it achieves the technological prowess to detect and communicate with others, or to manipulate its environment on a planetary scale. Now, let's pivot to some other explanations for the silence, ones that don't necessarily involve a great filter, but offer different interpretations of why we haven't heard a peep. Consider the zoo hypothesis. This idea posits that advanced extraterrestrial civilizations do exist, and they're aware of us. However, they've collectively decided not to make contact, observing us from a distance, much like we might observe animals in a wildlife preserve or a zoo. They might have a prime directive, a cosmic non-interference clause, believing that contact with a less developed civilization like ours could be detrimental to our natural development. Perhaps they have seen other civilizations collapse under the weight of cultural shock or technological disparity, and they've chosen to let us mature on our own terms. From their perspective, we might be too primitive to understand their intentions, or our current state of development might make us unstable. They might be waiting for us to reach a certain level of social or technological maturity, perhaps when we've solved our internal conflicts, achieved sustainable planetary management, or developed faster than light travel, before deigning to reveal themselves. The silence, then, isn't an absence. It's a deliberate, calculated non-communication, a cosmic quarantine zone around Earth. This hypothesis is intriguing because it shifts the burden of explanation from our rarity or their non-existence to their choice. It paints a picture of a universe that isn't empty but managed, overseen by entities far beyond our current comprehension. It implies a hierarchical structure to cosmic civilization, with us at a lower rung, still in the learning phase. The biggest challenge to the zoo hypothesis, of course, is explaining how such a vast array of alien civilizations could maintain such a perfect, unbroken consensus of non-interference over potentially millions of years. Even among us humans, maintaining a global consensus on anything is incredibly difficult, let alone for entire species spanning light years. And then there's the truly unsettling dark forest hypothesis. This concept, popularized by Chinese science fiction author Liu Cixin, takes a much more cynical and terrifying view of the universe. Imagine the cosmos as a vast dark forest filled with countless hunters. Each hunter is a civilization, and they are constantly listening, trying to detect any sign of another. But when they do detect a signal, they don't respond with a friendly hello. Instead, their immediate and logical response is to eliminate the detected civilization. Why? Because in this dark forest, there's no way to know the intentions of another hunter. Any civilization capable of interstellar travel or communication is also capable of the immense destruction. Resources are finite and the universe is vast but not infinitely so. To reveal your presence is to invite potential competition, enslavement, or annihilation. Therefore, the safest strategy for any civilization is to remain absolutely silent, hide your presence, and if you detect another, preemptively destroy them before they can destroy you. In this scenario, the cosmic silence isn't a sign of absence or a benevolent observation, but a deafening testament to universal fear and paranoia. Every civilization is a potential threat, and the universe is a place where showing your hand is a death sentence. Our own broadcasts, our attempts to reach out with SETI, search for extraterrestrial intelligence signals, would not be seen as a gesture of peace, but as a foolish act of self-annihilation, like shining a flashlight in a dark forest filled with predators. If the dark forest hypothesis is true, then the Fermi paradox isn't a paradox at all. The reason we haven't heard from anyone is precisely because everyone who could send a signal has learned the hard way not to, and those who are listening are doing so in absolute terrifying silence, ready to strike. It presents a stark and brutal reality, one where the very act of seeking contact could be the trigger for our own demise. So where does this leave us? Staring out into the cosmic night. The silence, once merely an absence, now resonates with profound possibilities. Is it the silence of rarity, implying a past great filter that we miraculously overcame? Is it the ominous quiet before a future great filter, a challenge that awaits us? Or is it the deliberate silence of a cosmic zoo? Or the chilling quiet of a predator-filled dark forest? Each of these hypotheses offers a radically different perspective on our place in the universe. If the great filter is behind us, we're incredibly special, but burdened with the responsibility of preserving this rare spark of life. If it's ahead, we must proceed with caution, understanding the perils of our own technological advancement and the external threats that loom. If it's the zoo hypothesis, we are being watched, judged, perhaps even nurtured, and our destiny might not be entirely our own. And if it's the dark forest, then every signal we send, every attempt to break the silence, carries an unimaginable risk. Regardless of which, if any of these explanations hold true, one thing becomes abundantly clear. Earth is an astonishingly unique and precious jewel. Its complex interwoven conditions allowing life not just to exist but to flourish and evolve into conscious beings are a marvel. This journey through the Fermi paradox and its potential solutions deepens our appreciation for our home world, transforming the cosmic silence from an enigma into a profound testament to Earth's rarity and the intricate, delicate balance that sustains us. The search continues, of course. We continue to build more powerful telescopes, develop more sophisticated detection methods, and refine our understanding of what life might look like beyond Earth. But as we do, we carry with us these profound questions, these chilling possibilities. They shape not only how we search, but why we search, and perhaps more importantly, what it means to be here, gazing out at the stars. What responsibilities do we bear, knowing the potential answers that the cosmic silence might hold? Next time on Dreamy Science, we'll dive into the cutting-edge technologies and ambitious future missions designed to push the boundaries of our search and explore how these profound philosophical questions are influencing the very frontiers of astrobiology and space exploration. Until then, keep looking up and keep wondering. The universe has many more secrets to reveal. Welcome back, cosmic adventurers, to Dreamy Science. We've journeyed through the astounding scale of the universe, grappled with the intricate Goldilocks conditions that make Earth so precious, and confronted the chilling possibilities of the Fermi paradox, the great filter, the zoo hypothesis, the dark forest. Each proposed solution, whether it suggests our incredible rarity or the terrifying dangers of the cosmos, ultimately leaves us with a profound sense of isolation and a heightened appreciation for our blue marble. The silence, you see, is deafening. Billions upon billions of stars, countless potential planets, and yet nothing. No definitive signal, no clear image of another technological civilization, no undeniable proof of life beyond our own. It's a mystery that tugs at the very fabric of our understanding, forcing us to ask, are we truly alone, or are we simply looking in the wrong places, at the wrong times, or even for the wrong things? Today, my friends, we are going to challenge our own assumptions. We're going to step outside the comfortable confines of Earth-like and human-like and ask, what if the reason we haven't found them is because we don't even know what them looks like? Think about it. Our entire search from the earliest radio telescopes to the cutting-edge James Webb Space Telescope is inherently biased. We search for biosignatures that resonate with Earth's biology, oxygen, methane, water vapor. We look for planets orbiting in the habitable zone of their stars where liquid water could exist on the surface. We imagine civilizations broadcasting radio signals, much like we did. We're essentially holding up a mirror to ourselves and expecting to see an alien reflection. But what if life, and indeed intelligence, is far more diverse, far more alien than our wildest imaginings? Let's begin by breaking down our definition of Earth-like. We've established that the conditions for Earth-like life are astonishingly specific. A stable star, a planet of just the right size, a molten core, plate tectonics, a large moon, a protective Jupiter, liquid water, a carbon-based chemistry. This is the recipe that worked here. But is it the only recipe? Consider the extremophiles right here on Earth. These are organisms that thrive in environments we once thought utterly uninhabitable. We're talking about microbes living deep within volcanic vents on the ocean floor, enduring crushing pressures and superheated toxic chemicals. We have bacteria that flourish in highly acidic pools, archaea that survive in frigid Antarctic ice, and organisms that can withstand staggering doses of radiation. These aren't just surviving, they're thriving. They laugh in the face of our conventional definitions of habitable. If life on Earth can be so incredibly adaptable, so resilient, so diverse in its requirements, then why do we assume extraterrestrial life must adhere to our narrow carbon and water blueprint? What if life can be silicon-based, using ammonia or methane as a solvent instead of water? The chemistry might be slower, perhaps requiring different temperatures, but is it impossible? Our universe is a grand chemical playground, brimming with possibilities we might not yet comprehend. Imagine life forms that don't need a star at all, deriving energy from geological processes deep within a rogue planet, adrift in the cold vacuum between galaxies, or perhaps life forms that exist as vast, diffuse clouds of self-organizing plasma in a nebula. The very fabric of our understanding of life might be far too restrictive. And then there's the question of time. We've talked extensively about the immense distances in space, but let's not forget the staggering stretches of cosmic time. The universe is nearly 14 billion years old. Our solar system formed about 4.6 billion years ago, and complex life on Earth has only existed for a fraction of that time. Humanity, as a technological civilization capable of broadcasting signals and building telescopes, has been around for a mere blink of an eye, a few centuries at most. Imagine a grand cosmic play unfolding across billions of years. Civilizations could rise, flourish, and fall long before our sun was even born. Others might emerge billions of years in our future, long after humanity has faded from existence. We are looking at a snapshot of the universe right now. What are the odds that another technological civilization, one that is also broadcasting signals in a way we can detect, exists at the exact same moment as us within our detectable range? It's like trying to catch two fireflies blinking in a hurricane. But those fireflies only blink for a second every million years. The temporal window for detecting intelligent life could be incredibly narrow. Consider the possibility of civilizations that have simply passed beyond our ability to detect them. What if an advanced civilization, after millions of years of technological evolution, transcends its physical form entirely? Imagine a civilization that has uploaded its consciousness into vast planet-sized supercomputers or diffused its intelligence across an entire star system, existing as pure energy or information. How would we detect something so utterly alien, so far removed from our biological origins? Think about the concept of a Type 3 civilization on the Kardashev scale. A civilization that has harnessed the entire energy output of its galaxy. Such an entity might be so vast, so powerful, and so fundamentally different from anything we can conceive that its presence would be utterly invisible or incomprehensible to us. Their communication might not be radio waves, but rather gravitational waves or quantum entanglement, or something we haven't even dreamed of. Their structures might be so colossal, Dyson spheres or even entire Dyson swarms enveloping stars, that we might mistake them for natural phenomena or simply not recognize them as artificial. We might be looking directly at evidence of their existence and simply not have the framework to understand what we're seeing. Perhaps they have moved beyond the need for physical bodies, existing as pure information within a simulated reality, or have simply chosen to optimize for efficiency, minimizing their energy footprint to the point of being undetectable. Why would a truly advanced civilization waste energy broadcasting signals across light years if they have no need or desire to communicate with nascent civilizations like ours? Their priorities, their goals, their very nature could be so fundamentally different from ours that we wouldn't even register on their radar, or vice versa. This line of thinking leads us to a fascinating and somewhat humbling conclusion. The absence of evidence for Earth-like planets or alien life might not be evidence of absence at all. Instead, it might be a profound testament to the limitations of our current technology, our anthropocentric biases, and our incredibly short history as a species capable of looking out into the cosmos. We are still infants in the universe, just beginning to crawl, while other civilizations might have already run marathons, built empires, and then dissolved into something utterly incomprehensible. So where does this leave us? Does it mean we should give up the search? Absolutely not. Instead, it means we must expand our imaginations. We must design new instruments, develop new theories, and challenge every assumption we hold dear about life, intelligence, and civilization. The search for extraterrestrial life is not just a scientific endeavor. It's a philosophical journey that continually forces us to reevaluate our place in the cosmos, to question what it means to be alive, and to confront the vast, beautiful, and sometimes terrifying possibilities of the universe. The mystery deepens, doesn't it? The cosmic silence, once merely perplexing, now seems to whisper of untold wonders and unimaginable forms of existence, stretching across unfathomable distances and epochs of time. We haven't found them yet, not because they don't exist, but perhaps because we simply haven't learned how to truly see them. Next time on Dreamy Science, we'll explore the profound implications of this expanding perspective for humanity. What does it mean for our future, our technology, and our very identity to search for something we might not even recognize? Join me as we continue our journey into the magnificent unknown. Welcome back, Dreamy Science Explorers, to our continuing journey through the most profound mysteries of the cosmos. As you're listening, I want you to cast your minds back to our last conversation, that tantalizing yet unsettling thought that perhaps the reason we haven't found any Earth-like planets, or more importantly, any definitive signs of life, isn't just because they're rare or hidden by a great filter. What if it's because our very definition of life is holding us back? What if in our cosmic search we're essentially looking for a mirror image of ourselves, failing to recognize something utterly, gloriously, unimaginably alien? We've talked about anthropocentrism, the human-centric bias that colours our perception. It's a natural inclination, isn't it? When we imagine alien life, we tend to picture creatures with eyes, limbs, perhaps even a language we might, with effort, decipher. We envision planets with liquid water oceans, oxygen-rich atmospheres, and temperatures that wouldn't boil or freeze us solid. We search for biosignatures like oxygen, methane, and water vapor in exoplanet atmospheres, because those are the telltale chemical fingerprints of life as we know it, here on Earth. But what if life, out there in the boundless tapestry of the universe, plays by an entirely different set of rules? What if the canvas of existence allows for colours we haven't even conceived? Let's do some quick mind-bending arithmetic. Our biology, our very existence, is carbon-based. Carbon is incredibly versatile, forming long, complex chains and rings that are perfect for building the intricate machinery of life. And water? It's an unparalleled solvent, allowing molecules to interact and react, a cosmic dance floor for biochemistry. But are they the only game in town? Imagine, if you will, a world where the very foundations of life are radically different. What about silicon-based life? Silicon, like carbon, can form 4 bonds, allowing for complex molecular structures. The challenge, of course, is that silicon compounds tend to be much less stable than carbon compounds, especially at Earth-like temperatures. Silicon-based life might thrive in environments we'd consider hellish, perhaps on planets with extreme heat and pressure, where silicates could remain molten and reactive. Or maybe, instead of water, the solvent of choice is liquid ammonia, which remains liquid at incredibly low temperatures, far colder than anything on Earth. Picture an ammonia ocean teeming with alien creatures under a sky of methane clouds. Or what about methane itself, in liquid form, acting as a solvent on a frigid world like Titan, Saturn's largest moon? Our telescopes, even the most advanced ones like the James Webb Space Telescope, are designed to detect atmospheric compositions. They look for specific absorption lines, the unique chemical fingerprints left by gases like oxygen, ozone, methane, or water vapor. But if life is silicon-based or ammonia-based, or thrives on completely different chemical reactions, its biosignatures might be entirely foreign to our current understanding. We might be looking directly at a planet teeming with vibrant, thriving ecosystems and simply classify its atmosphere as unremarkable or geologically active, completely missing the alien biology that's shaping it. It's like trying to find a specific type of exotic bird by listening only for the barks of dogs. We're listening, but perhaps for the wrong sounds. This brings us to a crucial pivot in our search. If biosignatures are so elusive, so potentially biased by our own blueprint, what about technosignatures? This is where the venerable search for extraterrestrial intelligence, or SETI, comes into play. If advanced civilizations exist, perhaps they leave behind not just the chemical byproducts of their biology, but the unmistakable fingerprints of their technology. What would those fingerprints look like? The most iconic image, of course, is radio signals, purposeful broadcasts sent across the interstellar void. For decades, SETI projects have been sweeping the skies, listening for any pattern, any modulated signal that screams intelligence above the natural cosmic static. We're essentially tuning our cosmic radio, hoping to pick up a station from another star system. But the challenges here are monumental, perhaps even more so than detecting alien biochemistry. First, distance. Even at the speed of light, radio signals take years, decades, centuries, or even millennia to cross the vast gulfs between stars. A signal we pick up today might have been sent when dinosaurs roamed the Earth, or even before our sun was born. And any response we send back would face the same agonizing delay. It's a conversation played out in cosmic slow motion, if it happens at all. Second, directionality and timing. Are alien civilizations broadcasting omnidirectionally, like a lighthouse sending its beam in all directions, or are they targeting specific stars, specific regions of space? And if they are they targeting OES? Are we in their beam? The universe is unfathomably vast, a cosmic haystack where our solar system is less than a single, microscopic speck of dust. If we imagine a civilization broadcasting, it's like a single firefly blinking in a hurricane, hoping someone thousands of miles away happens to be looking in exactly the right direction at exactly the right second. And civilizations, like stars, have lifespans. They rise, they flourish, they fall. Are we listening at the right time in their cosmic history, or are we tuning into a channel that went silent 1 million years ago? Third, frequency and bandwidth. The radio spectrum is enormous, stretching from extremely low frequencies to incredibly high ones. SETI programs have made educated guesses about which frequencies might be universal. Perhaps the 21 centimeter line of neutral hydrogen, a fundamental constant of the universe. But what if we're wrong? What if they communicate using X-rays or neutrinos, or even gravitational waves, which we're only just beginning to detect? It's like searching for a specific book in a library that contains billions of volumes without knowing the title, the author, or even the language it's written in. And fourth, decoding. Even if we do detect a signal, how do we interpret it? Would it be a simple prime number sequence, a universal language of mathematics? Or would it be encoded in a way that reflects their unique biology, their history, their philosophical outlook? Concepts utterly alien to us. Imagine trying to understand a message from a civilization that doesn't perceive time linearly, or that has 20 different genders, or communicates through symbiotic fungal networks. Our human minds, with all their brilliance, are still fundamentally constrained by our own experiences. Beyond radio signals, what other technosignatures might exist? Perhaps the grandest idea is that of megastructures, colossal engineering projects built by advanced civilizations to harness the energy of their star. A Dyson sphere, for instance, a hypothetical structure that completely encloses a star to capture its entire energy output, would profoundly alter the star's light signature. It would dim the star or cause it to emit excess infrared radiation, as the sphere itself radiated away waste heat. We are looking for these anomalies, and have found some intriguing though ultimately natural candidates, like Tabby's star, which briefly caused a stir. But again, the scale of such an undertaking is so immense that detecting one, even if it exists, is a monumental task. What about artificial light pollution? If a civilization becomes truly advanced, its night side would glow with artificial illumination. We can already detect the faint glow of Earth's cities from space. Could we detect the cities of an alien civilization on a distant exoplanet? Perhaps, with future telescopes, but the challenges of resolution and signal strength are staggering. This leads us back to the profound cosmic silence. Is it truly a silence of emptiness, or a silence imposed by our own limitations, our own biases, and the sheer mind-boggling scale of the universe in both space and time? Perhaps the universe is teeming with life, with civilizations, with wonders beyond our wildest dreams. But they are either too far away, too different, too fleeting, or too deliberately quiet for us to perceive them with our current tools and our current understanding. The silence, therefore, isn't just a lack of data. It's a profound challenge to our imagination. It forces us to confront the possibility that the universe is far stranger, far more diverse, and far more complex than we can currently grasp. It reminds us that our search for life is not just a scientific endeavour, but a philosophical one, constantly pushing the boundaries of what we define as life, intelligence, and even existence. In our next chapter, Dreamy Science Explorers, we'll delve deeper into this philosophical rabbit hole asking, what if intelligence doesn't manifest in ways we recognize at all? What if it's not biological or even physical in the way we understand? What if the life we're seeking is so utterly alien that it transcends our very ability to perceive it? Get ready for another mind-bending exploration into the ultimate cosmic questions. Welcome back, cosmic explorers, to Dreamy Science. We've journeyed through the astounding complexity of Earth's habitability, peered into the chilling possibilities of the Great Filter, and dared to confront our deepest anthropocentric biases. We've considered life that might be silicon-based, swimming in methane oceans, or existing as pure information, silently weaving through the fabric of space-time. We've acknowledged that our current search for technosignatures is like trying to hear a whispered secret across a cosmic ocean, further complicated by the sheer vastness of space and time. But what if the silence isn't just about what we're looking for, or how alien life might manifest? What if the great silence we perceive is, at least in part, a reflection of the profound limitations and inherent biases in how we're currently conducting our search? What if we're not just looking for the wrong kind of needle, but we're also searching in the wrong haystack with the wrong kind of magnet? Let's delve into this, shall we? Because the challenges we face in finding extraterrestrial intelligence aren't solely about the nature of alien civilizations, they are profoundly about the nature of our search. Think about it. For decades, the primary method for searching for extraterrestrial intelligence, SETI, has largely focused on listening for radio signals. We point enormous dishes into the sky, patiently sifting through cosmic static, hoping to catch a patterned pulse, a modulated message, a clear hello on a specific frequency. And why radio? Because that's our primary long-distance communication method. It's what we use to broadcast our presence into space. It's relatively inexpensive, travels at light speed, and isn't easily absorbed by interstellar dust. It makes perfect sense. For us. But what if advanced civilizations don't use radio waves at all, or only use them for a fleeting moment in their evolutionary history? Imagine trying to communicate with an ancient Roman legion using a smartphone. The technology gap isn't just vast, it's practically incomprehensible. What if they've moved on to communication methods we can't even conceive of yet? Consider the possibilities. Neutrinos. These ghostly particles pass through matter almost unimpeded. Could they be a preferred method for interstellar communication, offering a way to send information without the interference and absorption issues of electromagnetic waves? We're only just beginning to understand how to detect and harness neutrinos, gravity waves, ripples in space-time itself. An advanced civilization might be able to manipulate space-time in ways that allow for instantaneous, or at least highly efficient, communication across vast distances, We've only just confirmed their existence a few years ago. Quantum entanglement. The spooky action at a distance. If two entangled particles can instantly influence each other, regardless of separation, could this be harnessed for FTL, faster than light communication? This pushes the boundaries of our current physics, but can we truly say it's impossible for a civilization millions of years ahead of us? Other dimensions or realms. What if communication isn't even happening? Within our perceived three spatial dimensions, plus time, what if advanced beings communicate through subtle shifts in the fabric of reality that are entirely invisible to our current instruments and understanding? The point is, our radiocentric search is a profoundly anthropocentric assumption. We are projecting our current technological capabilities and preferences onto hypothetical alien species. It's like a deep-sea diver searching for other divers, but only looking for scuba tanks and flippers, completely missing the bioluminescent creatures, the chemosynthetic ecosystems, or the incredibly complex communication systems of whales, simply because they don't fit our preconceived notions of aquatic intelligence. And it's not just what we're listening for, it's where we're listening and when. Our current exoplanet searches, while incredibly fruitful, are still biased. We primarily look for planets around stable, long-lived stars like our Sun, G-type stars. We're getting better at finding planets around smaller, cooler M-dwarf stars which are far more numerous in our galaxy. But even then, we're looking for planets in their habitable zones, which, as we've discussed, is a deeply complex concept. What about rogue planets, those interstellar wanderers not bound to any star? Could life evolve in their internal oceans warmed by geothermal vents? What about gas giants with habitable moons, perhaps even moons with thick atmospheres and subsurface oceans? We're only just beginning to consider these possibilities, let alone develop the technology to thoroughly search them. Our search space, while seemingly vast, is actually a tiny, well-lit corner of the cosmic ballroom. Then there's the when. The cosmic timescale is mind-boggling. Our universe is 13.8 billion years old. Earth formed about 4.5 billion years ago. Complex life has only existed for a fraction of that, and intelligent, technologically advanced life, capable of broadcasting signals for a mere blink of an eye. Imagine two ships passing in the night. One broadcasts a signal for 5 minutes every million years. The other ship might pass by listening intently, but if their listening window doesn't perfectly align with that 5-minute broadcast, they'll hear nothing but static. Now scale that up to billions of years, billions of stars, and potentially millions of different civilizations, each with their own unique, fleeting technological windows. The chances of our brief technological era overlapping with another civilization's broadcast, and us pointing our dishes in the right direction, at the right frequency at the right time, become astronomically small. It's not just a needle in a haystack, it's a needle that only exists for a microsecond, in a haystack that's constantly being remade. This temporal filter is a significant challenge. Civilizations rise and fall, they might develop advanced technology, broadcast for a few millennia, then collapse due to internal strife, environmental catastrophe, or simply evolve beyond the need for radio communication. We might be listening to a graveyard of ancient whispers, long faded into the cosmic background noise. Or perhaps we are too early, listening to a universe still largely in its infancy, waiting for the majority of life to emerge. So when we perceive the great silence, is it truly an absence of life? Or is it merely the profound silence of our own limited perception and search strategies? This realization isn't meant to be disheartening, Quite the opposite. It's an invitation to broaden our imaginations, to push the boundaries of our scientific inquiry, and to challenge our own assumptions. The silence isn't a dead end. It's a profound mystery begging for a more expansive approach. What does a more expansive approach look like? First, it means diversifying our search methodologies. We need to invest in technologies that can detect non-radio signals, neutrino detectors, gravity wave observatories, perhaps even entirely new physics that allows us to probe quantum phenomena across interstellar distances. We need to think beyond sending messages and consider leaving traces. Second, it means looking for anomalies, not just expected patterns. Instead of searching for something that looks exactly like our signals, what if we look for anything that simply doesn't look natural? Imagine a star that dims and brightens in an impossibly regular non-astrophysical pattern, or a galaxy that shows an energy signature that defies known stellar processes. These could be the subtle fingerprints of vast, planet-spanning or even star-spanning engineering projects, what we sometimes call techno-signatures on a grand scale, like Dyson spheres or stellar engines. These megastructures, if they exist, would fundamentally alter the observable properties of stars or even entire galaxies. We're talking about looking for the cosmic equivalent of a perfectly straight line in a forest of swirling organic curves. Third, it means leveraging advanced computational power and artificial intelligence. The sheer volume of data we collect from space is staggering. Human brains, even brilliant ones, are prone to bias and can only process so much information. AI and machine learning algorithms, however, can sift through petabytes of data, identifying subtle patterns, anomalies, and correlations that would be invisible to us. They can learn to distinguish between natural cosmic noise and potential artificial signals, even if those signals don't conform to our predefined notions of what a message should look like. They could even help us design entirely new search protocols based on emergent patterns in the data we haven't yet recognized. Fourth, it means cultivating a truly interdisciplinary approach. The search for life shouldn't just be the domain of astronomers and astrophysicists. We need biologists, chemists, computer scientists, philosophers, linguists, anthropologists, and even artists to contribute. Each discipline brings a unique perspective, a different way of thinking about what life is, how it evolves, how it communicates, and how it might leave its mark on the universe. Perhaps a linguistic expert could identify patterns in cosmic noise that resemble language, even if it's not radio. Perhaps an anthropologist could predict how a truly alien society might interact with the universe around it. The Great Silence, therefore, isn't a definitive statement about the rarity of life. It's a profound challenge to our ingenuity, our creativity, and our ability to transcend our own terrestrial limitations. It's a cosmic mirror, reflecting back to us not the absence of others, but the boundaries of our own perception. The universe is an unimaginably vast and ancient place. To assume that life, if it exists, would conform to our narrow definitions, communicate by our methods, or exist within our fleeting temporal window is to severely underestimate the boundless possibilities of cosmic evolution. This journey of discovery, this quest to understand why we haven't found any Earth-like planets or definitive signs of alien life, is not just about finding answers out there. It's also deeply about understanding ourselves, our place in the cosmos, and the astonishingly unique conditions that have allowed us to ask these questions in the first place. The silence isn't an end, it's a beginning. It's an urgent call to expand our minds, our tools, and our very definition of what it means to search for life in a universe brimming with unfathomable wonders. So, the search continues, dear listeners. It continues not just outward into the starry expanse, but also inward into the depths of our own assumptions and biases. And in the next chapter, we'll delve even deeper into the profound philosophical implications of this ongoing quest, exploring what it truly means for humanity to be alone, or to be part of a cosmic tapestry we're only just beginning to perceive. Until then, keep dreaming, keep questioning, and keep exploring.